Our next topic is Primality Test. So when we talk about RSA, by the way, RSA is the initials of the last names of the authors who discovered this algorithm, Rives, Shamir, and Adelman. So recall that the first step of the key generation algorithm of RSA starts with choosing two big random prime numbers. So question is how you can choose two big prime numbers. So you need a test to check if a number is prime or not. So P and Q should be generated randomly. In standards, a random number generator, which is a combination of a physical random number generator and a deterministic random number generator, is used. So you already know from our discussion of randomness a few weeks ago. But the question is how you can choose such a, when you randomly generate a number, what is the probability that it is a prime number? So assume that you randomly generated a 512-bit number. So if it is even, then of course it is not prime because it can be divided by 2. But if it is odd, what is the probability that it is a prime number? And for this length, it is approximately 1/355. So you should be very lucky to choose a random 512-bit integer and hope that it is a prime number. And if it is not prime, by the way, then RSA won't work. Your system can be broken. So this is why we have to be sure that the numbers we are choosing are prime. So what we need to do is to randomly choose such a randomly generate such an odd integer and then apply primality test and check if it is prime or not. So question is, do we have a polynomial time algorithm for primality? So is there a decision algorithm that runs in polynomial time and answers you as if the result is prime or not? So this was an open problem for a long time, but in 2002, Agrawal, Kagal, and Saxena provided a polynomial time algorithm to test primality. So it is known as AKS algorithm. But the problem is that although it is a polynomial time algorithm, the operations performed there are not simple arithmetic operations. There are many things to be done. So it is really slow in practice. So this is why we cannot use it. And this is why actually we still have largest prime number search competitions. Because if this algorithm were fast, we can always check more and larger odd integers and say that if it is prime or not. So if this is too slow for us to use in cryptography, what we do is as follows. We use randomized polynomial time algorithms instead. So let's see how they work. In order, of course, first maybe we should define what we should see what kind of different type algorithms we have. So let's start with the Monte Carlo algorithm. Let's define what it is. A yes-biased Monte Carlo algorithm is a randomized algorithm for a decision problem for which the yes answer is definitely correct and the no answer is incorrect with a probability at most epsilon. So actually these are the type of algorithms that we use for primality testing. The algorithms I will define in the following slides will, when they say that this number is a composite number, then it is definitely a composite number. So it is a yes biased in this way. But if the algorithm cannot determine if it is a composite number, then the algorithm will tell you that it is prime, but this answer would be correct with probability around 3/4 or something. So we will see an example in a minute. But we also have Las Vegas type algorithms. A Las Vegas algorithm to answer a decision or search problem is an algorithm whose answer is definitely correct, but if it finishes. So the algorithm may run indefinitely. So these are two different types of algorithms, but we will be seeing Monte Carlo algorithms now. So let's start with Fermat test for primality. So given a node n, we are trying to decide if this number is prime or not. So assume that we are dealing with RSA, so we choose a random odd integer, and now we want to see if it is prime or not. So what we can do is as follows. We can randomly choose a number a and compute the a to the power n minus 1 modulo n, and check if it is equals to 1 or not. Because remember that when n is prime, this is always the case. But if n is not prime, sometimes this might be the case. So if when you check this, if the answer is not 1, then we can say that n is definitely a composite number. So then what you need to do is the randomly generating another number and check if this is the case again. But if you're unlucky, n might be composite, but this result is somehow correct for your choice of a. So what you do next is choose another a and perform this operation over and over again. So if this equals to 1, the test outputs prime, but this answer is true with some probability. So choose another a, perform this operation a lot of times. But we have a little bit better test than Fermat test, which is Solovay-Strassen test. And this time they use Euler's theorem. So instead of checking this, they check if Euler's theorem is correct. So almost the same thing, but this time you check the Legendre symbol here. So again, if this is not correct, it doesn't equal to this, then n is definitely a composite number. But if this is the case, and the test will tell you that n is prime, so the test outputs prime, but this answer is true with probability less than 1 over 2, but close to 1 over 2. So you can use these algorithms, but there is a Miller-Rabin algorithm which actually combines both of these ideas, but it would be a little bit confusing to write the whole algorithm, so I will just mention what it is. Miller-Rabin algorithm actually uses these similar ideas, and the answer composite is definitely correct, and the answer prime is false with probability 1 over 4, which is a really good thing. So what you do is repeat this process many times. So if the test answers m times n is prime in succession, then the probability that n is composite is less than or equal to 1 over 4 to the power m. So in your test, you randomly choose the number a m times, and if all of them the test tells you the result is prime, then you might be unlucky and it might be a composite, but that would happen with probability less than or equal to this. So if you repeat this test 25 times, then n is prime with and if all in 25 times the number passes this test, then we will say that it is prime with probability 1 minus 1 over 2 to the 50. So as you can imagine, the result will be 0.99999. So it is very close to 1. So, but if you're paranoid, instead of applying the test 25 times, you can apply 30 times or 40 times just to be sure. And this probably would converge to 1 when you perform infinitely many trials. So this is actually what we do in practice. So in practice, when somebody is using RSA, they randomly generate an odd integer and they perform Miller-Rabin algorithm like 25 times. And if all of the cases the algorithm returns you that it is prime, then you can have confidence that it is prime, because the probability that it is not a prime is really small, which is very close to 0. So this is actually what is performed when you generate a certificate or when you choose RSA parameters. In the background, the system randomly generates these prime numbers and they check if they are prime by using Miller-Rabin algorithm.